axis. So the shape of the tolerance zone will be a cylindrical tolerance zone. So here you can see the deviation at right hand side. The deviation is more, so it went out of this zone, so it is out of spec. So next, tolerances of location. So in location, we have a true position, concentricity, and symmetry. So these are the tolerance zone shape with respect to the feature. For cylindrical feature, the zone will be cylindrical tolerance zone. So for the plane, parallel plane tolerance zone, and for the spherical, so it will be the spherical tolerance zone. So here you can see the concept is with respective to this origin. The origin is here. With respective to the origin, we're going to check whether this hole is located in correct location or not. We're going to calculate that. So here in this drawing, you can see the shape of the zone. The feature is cylinder, so the tolerance shape of the tolerance zone will be cylindrical. So in this view, you can clearly see here in this corner is the origin point. When we align according to this datum ABC, we can get this corner as a origin, and then this small circle is a circular tolerance zone. So the offset of the hole should lie in between this small circular zone. So the size will be 1.5. Here they have mentioned in this feature control frame. So at the right side, you can see in zoom clear view. Here, this is a theoretical exact center point. This center point is the offset, actual value placed in the part. So here x offset is called as del x, and y offset, y deviation is been called as del y. So we're going to calculate the overall deviation will be z. So here this is the true position formula. Z means overall deviation. Z is equal to 2 into square root of del x square plus del y square. So Z will be the total radial deviation, and del x is the x measured deviation, not x value. It is a measured deviation, and y is a del y is the y measured deviation. So the measured deviation can be calculated with a difference of nominal and actual. So if we minus nominal and actual, we can get the deviation. So here in this picture, you can clearly see the offset. The dotted circle is the exact part. So it has some offset. We're going to calculate that offset. So for x distance 10 mm, the actual is 10.4, and for y 10 mm, actual is 10.3. So here the deviation of x is 0.4 and the deviation of y is 0.3. So we're going to substitute this value in this formula, and when we calculate this, then we can get this 0.98. So the exact offset z overall radial deviation is 0.98. So it is lesser than this given GD&T tolerance. So it is said to be located inside this zone. So the part is within spec. So if the value is larger than this tolerance zone, then it is out of spec. So now we're going to see the position with modifiers. Modifiers means we're going to calculate the position with MMC condition and LMC condition. MMC means maximum material condition. LMC means least material condition. So for MMC, they will give M. For LMC, they will give L. So here MMC is 13.5. So in MMC for hole, smallest allowable diameter will be the MMC. Because when the hole get smaller, then the material will be added. So in smaller hole, the material will be at maximum. So it will be MMC. In LMC, it is opposite. In largest, when the hole get bigger, then the material will be reduced. So the material will be in least condition. So for LMC, largest allowable dia will be LMC. So for the shaft, it is opposite. So for shaft, MMC will be largest allowable diameter. If the shaft dia gets bigger, then the material will be added. The material will be in maximum condition. So MMC will be the largest allowable dia. In LMC, similar opposite, smallest allowable dia will be the LMC. When we remove the dia size in the shaft, so the material will be reduced. So the material will be in least condition. So for LMC, smallest allowable dia will be the value. So here in this condition, you can see this is the actual dia. Sorry. So this is the actual dia, 0.4, but MMC is 13.5. So the manufacturer manufactured the dia for 14.4. So the hole is bigger, so it has more clearance. So due to this clearance, it has more possibility to fit. Even the position is went out of spec. Here you can see the actual position is 1.8. So for this manufactured dia, we're going to see with MMC condition, we can get here the clearance value. So the clearance will be called as bonus tolerance. So here BT means bonus tolerance. Bonus tolerance formula is actual dia minus MMC. If we minus actual dia and MMC, we can get this clearance value. So this clearance value will be going to added in this GD&T tolerance. So here the value is 0.9. So the 0.9 should be added in this GD&T tolerance. So for MMC material condition with respect to this actual diameter, the tolerance will be 1.9. So the actual position is 1.8. So it is within spec. So next, composite tolerance. So if there is any pattern like this 4 holes or 8 holes, it is followed in pattern, then they will give composite tolerance. Composite tolerance will be like this. Top they will give like normal with datums, and then bottom they will give like only a datum or a primary secondary datum they will give. So the rule of composite tolerance is without breaking this pattern distance, it can move right. So this is the tolerance zone. Within this tolerance zone, it can move right without breaking this pattern pattern distance, and left, and it can move up and down, and also it can move diagonally without breaking this pattern dimension 50 and 40. It can move below this tolerance zone. So also it can rotate without disturbing this tolerance pattern dimension. Here you can see in this hole, it is inside this tolerance zone, but the deviation is left side. Here you can see the deviation is right side. So here it is breaking this pattern. So it is not allowed. So in composite tolerance, without breaking this pattern dimension, it can move inside this tolerance zone evenly. So it is the rule for composite tolerance. Now we're going to see concentricity. Concentricity is same like position. Here the datum axis and the feature axis should be in same in line. So here we're going to see the variation, the offset. So the exact theoretical value should be 0, 0 for the feature. But here you can see in this dotted line, the variation is there. So we're going to calculate that variation. Same position formula will be applied in this concentricity also. So the X deviation is noted, and then Y deviation is noted. It should be substituted in this formula. If the Z value is lesser than this tolerance, then it is located inside this tolerance zone. If the Z value is greater than this tolerance, then the offset went above this tolerance zone. So same like position. Symmetry also same. So here you can see if they have extended this line and this thickness, in this thickness they have mentioned any datum, then the reference should be in mid plane we should take reference. For example, with respective to this plane and this plane, we can get a mid plane. So it will be the datum. So here for the same feature 2, here they have extended the line and they have given dimension, and there they have given this feature control frame symmetry. So we have to consider this mid axis. This plane and this plane mid axis will be considered. So both datum axis and this feature axis should be in same inline. So here also we're going to calculate the offset. Here only one deviation will be occurred. Either it should go up or it should go down. So only one axis deviation will be present. So here you can see the tolerance zone. Here the red line is derived line, actual line. Here you can see the tolerance. So sorry, the formula for this symmetry. So only del x is there. Why? Because it will vary only in x-axis. So only one axis will be there. So the z, if the z value is less than tolerance, then it is located inside the zone. If the z value is greater than this tolerance, then the derived point will be above this tolerance zone. So same in position, concentricity, symmetry. These three are same. So in 2018 update, they have removed concentricity and symmetricity. We can check symmetry and concentricity in position itself. We can check. So in 2018 update, ASME, they have removed concentricity and symmetry. So now we're going to came to the today topic, runout. So in runout, two runout are there: circular runout, total runout. So here at the left side, you can see the drawing. So this is the datum. The big cylinder is the datum. Here you at the top right, you can see the 3D view. For this smaller dia, they have given a runout symbol. Tolerance is 0.75. Datum is A. So the cylinder center axis is the datum. So we're going to check this cylinder runout. So here you can see this is the datum axis and this is the feature axis. So here the tolerance zone will be two concentric circle. So circular runout is a two-dimensional. So the tolerance zone is also a 2D. So it is act like two concentric circle. So the zone will be separated from the datum axis. So here you can see the side view. So the red dotted line is the tolerance shape. So here the waviness is there. So actual deviation, the waviness, the form of the feature should be lie within this tolerance zone. Same like circularity. And what the difference between circularity and runout is? Here is the twist. The offset is also will be controlled in runout, but in circularity only the form will be controlled, and in concentricity only the location will be considered mainly. Here in runout, the form as well as the location, both the parameters will be considered. Here you can see the dotted line is the offset, and you can see the part roundness variation. In 3D also you can see. So the manual method will be the datum axis is arrested and set to rotate in 360 degree with the dial gauge placed here and the readings will be noted. So if the readings comes below this tolerance, then it is okay. So if it went above this tolerance, then it is not okay. So each point of the features must be lie within this tolerance zone. Here you can see here offset is also happened in left hand side, and some roundness error is also there, but it is within this zone. So it is within spec. Here at the right side, roundness and this offset, considering this both, it went above this tolerance zone, so it is out of spec. So here you can see the CMM report for a circular runout. So this is the maximum point. The two red color circle is the zone, concentric circular zone, concentric circle. Two concentric circle is the zone. So here you can see the waviness, the graph, it is the deviation. So this is the maximum point and this is the minimum point. Here in left side, it is within spec. At right side here, you can see the two concentric circle, red line, red color circle. So here it went above this zone. So at the right hand side is the not okay. So next, total runout. So here total runout is a 3D type. So we're going to consider all the surface. So here you can see the shape of the zone, two concentric cylinder. So we're going to cover all the surface. So the zone will be two concentric cylinder. With respective datum axis, the shape of the zone will be considered. And in manual method, here in total circular runout, only rotation has been done. Here, the gauge is set to move in a linear axis. The datum should be arrested, and rotation 360 rotation will be there, as well as the dial gauge should move in a linear direction. So here in this case, the form of straightness will be added, as well as circular form deviation will be considered, and the orientation will be added. It will control the orientation, wobble wobble of this cylindrical feature, and also the location is also will be considered. So it controls the form of the feature and the location. It will control the location offset as well as orientation. So if the feature is tapered, then it should be lie within this zone. So these three parameters, total runout will be controlled. So this is the scenario where they have asked in plane total runout. So it is also called as axial runout. So here this is the datum. So the datum will be arrested in a chuck, and then part is set to be rotated in 360 degree. So here the dial has been placed in this plane, and here the form flatness form will be considered. In circular part, roundness form will be considered. Here orientation perpendicularity will be considered, and also the dial must be move in a linear direction, as well as the part should rotate, so that we can get the exact deviation of the total runout. Here there is a difference. So circular runout is a 2D type, total runout is a 3D type. So the tolerance shape will be two concentric circle. Here the shape will be two concentric cylinder. If it is plane, then the shape will be two parallel plane. That's all. Then circular runout, the concentricity plus circularity will be added. Here in total runout, the form cylindricity, location, as well as runout will be orientation will be added. So runout usually is put into the place when oscillation, vibration need to control on a fast rotating parts like engine or transmission. So if the part rotates, it's probably required runout. So here same, but we're going to consider the overall surface. So the thing like a large shaft transmission, and complex gear, all cases where the total runout will be used. So next, tolerance of profile. Here, profile of line and profile of surface will be there. So profile of line is a two-dimensional. So here in this drawing, you can see For this side plane, they have asked profile of line 1 mm with respective to the datum ABC. A is the primary datum, B is the secondary datum, and C is the territory datum. Here they have given targeted points. So in the next slide, you can see the shape of the zone. So it is a two parallel line. So within this two parallel line, the feature form location for this 50 mm, here the feature should be located in exact 50 mm. If there is any stock, it will go above this tolerance zone. So the form should be inside this zone. So the location should be inside this zone. And then if there is any orientation error, then for that also it will be go outside the zone. So the profile of line will control form, orientation, and then location. So here you can see the side view. So it is a two-dimensional tolerance zone existing of two parallel curves. So for example, here there is a line, so it will act like a two parallel line. If there is any curve at the right top bottom, sorry, right top, you can see the 3D view, it is a curve. So the tolerance will be like a two parallel curve. So it controls form relative to its feature, angle of the feature, as well as position from the data margin. So next one is profile of surface. So profile of surface is similar like profile of line. Here it is a 3D feature. So we're going to cover all over the surface. So same, you can see in this left hand side drawing. So it will be two parallel plane because the feature is plane. So the overall tolerance zone will be 0.1. Here the location has been mentioned. So with respective to this location and form and then orientation, the feature should be controlled within this tolerance zone. So it is a three-dimensional tolerance zone existing of two parallel surface curves that follows the contour of the surface profile across the entire length. This tolerance zone may or may not be referenced by a datum. So it can the datum will be given, and also sometimes they will not give datum. So what is the difference is, so if the datum has been given, so location, form, and orientation, all the three will be considered. If they have not given the datum, here you can see only 0.1 they have given. So only form will be considered. No location and orientation will be considered. With respect to the form, we're going to see the profile. It will control only the form and shape. Here you can see the other scenario. Here the part is curved. So with respective to this curve, the tolerance zone has been separated. Overall zone is 0.1. So here they have given two type of surface profile. For 0.5, they have given datum. And then below 0.1 is there without datum. For only form, we're going to check profile of surface. And then with respective to the datum, we're going to check the profile of surface. Here you can see this tolerance zone in side view. So with respect to the datum, it's going to consider a form, location, and orientation. Below for 0.1, only form will be considered. Here you can see for each and every point, distance will be there like 24.75. So for each and every point, the distance will be maintained. So if there is any deviation, then for location, it will go out of the tolerance zone, as well as the form of the shape is also should be correct. And then the angular spec of the pot is also should be like same in this form. If there is any angular deviation also, then it is said to be located outside this zone. So if the datum not given, only we're going to consider this shape and form. That's all. No need of location and orientation will be considered. So here you can see the CMM profile of line graph. Here the red line is the tolerance. So this black and the graph is the actual dimension in the part. So here it is within the tolerance zone. So the part is okay. Okay, that's all. We have finished the GD&T courses. So form, orientation, location, and then today we have covered runout and profile.